So let me start now. We continue from where we left last time. So we got the problem Lx equal to we had the for the interval 0 to with the initial conditions. Okay, the problem was Lx plus 2t 0 with the initial conditions x 0 equal to x 1. Its derivative 0. So the solution we have obtained, or the Green's function we have obtained, was this AST equal to 0 for, and this is equal to s minus t. Yeah. If you look at the graph of this, so this is supposed to be t interval, or if you can get this as s interval and t interval, then you see that the function is on 0 1 cross 0 1. This is s 0 1 cross 0 1. The function is defined to be s less than or equal to t. S less than or equal to t will be this portion. So here the function is defined as this. So over here you see that the function, the derivative of the function has a jump as continuity. As you can see the derivative is with respect to t is going to be minus 1, and this is 0 here, so there is a jump. Yes, we have described. Also, if you look at simply plot the graph of this, you see that. Yeah. Okay. Right. So what you have is this. If you look at this function, the graph of this function, let us plot this 0 to 1 as a function of t. Then you have, up to s. This is identically 0, and from then onwards, it is something else. This is this. So this is the key interval. You are plotting AST. So the graph of the function would turn out to this. And you can look at it as a function defined on the interval st. So you have AST defined on for all possible values of s and possible values of t. Then you see that the function is having a discontinuity over here, or its derivative is having a discontinuity. Okay. Along s equal to t, you see the function is smooth, it's continuous, not really differential. But the differentiability, the first derivative has a jump discontinuity. That is what we define as a function. Okay. Now let us go to some properties of this. Okay, I forgot anything. Okay, now let me go to look at the properties of the function kst. So the lemma is kst and its first n minus 2 derivatives are continuous for a less than or equal to s less than or equal to b, a less than or equal to t less than or equal to b. That means on AB cross AB. The same is true for the n minus first derivative except along s equal to t. When I put t here, I am differentiating with respect to, I am talking about the derivative with respect to t, or the partial derivative with respect to t. N minus 1, n minus first derivative so I am repeating it unnecessarily. Except this is what I marked here. This is 0 1 cross 0 1. Along this, the n minus first derivative has a jump discontinuity with respect to t. So let us prove this result. Give a proof of this lemma, because this is crucial, that it's a kst is a function of two variables and its differentiability and continuity properties are crucial to the essential proof of the theorem. So let us, what we do is we construct the equivalent system and then work with this. Okay. So we prove it as follows. S greater than t is this. So t, when t varies between a to s, that is what you mean by for s greater than t. Is identically equal to 0, and the lemma is trivial. Okay. Now what we are doing is
impose conditions at S which are different from the matching function that we have obtained. We see identically zero solution. So you have to show that they patch up smoothly. So let us take for that means t greater than or equal to S. This is the portion. Okay. Set derivative with respect to t of I minus first derivative. This is for I equal to, we are going to actually write down the system of these equations. Now then, what happens? Now you see I can write this way. Thus what will be the corresponding system? The first order system is the following. It is dx1 by dt equal to x2 standard one, d and dxn by dt is going to be equal to Pn, what is it? P This is the equation that you have on the interval S2. Okay. Now what one does is, this is the t variable. What you do is, so what is given is, on this one you have set up the system, this interval. What you do is you pull this to A by a change of variable. Okay. So what you do is you set tau equal to t equal to tau plus s minus a. So what you are doing is, you are writing this as in fact tau minus s minus a. You are just pulling this interval. So this interval is now mapped to some interval here. Okay, so what are the limits that you have? When t equal to s, why have to write it this way? Introduce the tau equal to t plus a minus s. This is the transformation. So not this one. So okay, what I do is, okay, let us find out what happens. When t equal to s, you get got that will change the variable. T plus S minus A, that's right. Then what happens? T equal to A okay. T equal to A okay. T equal to S corresponds to and T equal to B correspond to, because we are working on this interval, T equal to B corresponds to tau equal to what is it, T plus A minus sorry, T equal to B, then you are changing B equal to therefore tau equal to tau equal to B plus minus S, that's right, B plus A minus S. Okay, so we use this transformation. That amounts, you see that when T equal to S, you are getting tau equal to A. So the new variable is on the interval A to B plus A minus S, this interval. The variable is tau. Then what happens? See, dx by dt, dxi by dt is automatically equal to dxi minus by dt. Okay, therefore the set of equations transform to dx1 by dt and this will be simply dxn by d tau equal to minus pn tau minus P1 tau plus S minus A. They are all now functions of tau. Therefore, now we just to get rid of this tau from our discussion, we reset that is, this is the new t that is coming. Then we end up with the equations. Then the equivalent system is dxi by dt equal to minus 1 and dxn by dt equal to I am resetting tau equal to t, so this is equal to minus pn t plus s minus a p1 I just wanted to demonstrate how it comes. That is why I introduced the new variable tau. What I have done is I pull this interval all together here, so that S is now matched with A. There is the corresponding change that has taken place. You can geometrically conceive this. And what is the extreme end that you have? The extreme end becomes the B will go over to the corresponding B plus A minus S. So it is now on the interval B to on the interval A to, so A plus, clear, okay, it's A plus B minus S. That is the other extreme end that you have. Okay. So we have now a new system. Okay. Now you see that these are all continuous functions on this particular interval, because PIs are given to be continuous on the interval A to B. Therefore, in particular, this is also true. Right. Now consider this system on the interval this. Now set S2, S1 to be less than S2. Now we are trying to work out, to find out the continuity of the solution KST with respect to S. We have already with respect to t, we know that it has been so constructed that the function as well as all its n minus 2 derivatives are continuous, and even the n minus first derivative has a jump discontinuity. What happens with respect to S? Can you say the same thing? Because see, we have got KST is defined not only for a particular S, but for all S belonging to the interval AB. So we want to study the continuity of that on this interval. Okay. Then the initial conditions are whatever we have set up at S will be the corresponding conditions at A, are Okay, so we have this one. I'll write it this way. We are now working the system. So XIA and you have XNA minus, that is you set P equal to A. Then this is the initial value problem that we are considering. We set S1 less than S2. Then what are the solutions? Set treat S as a parameter. Okay, so these are the functions. So that parameter is coming into the picture and they are satisfying the same set of this set of conditions for each S. Now corresponding to, and also now set S is equal to S1 in this system. And we have taken S1 less than S2. Right. Then look at the case, the solution XS2T. Satisfies the system with the initial conditions given there. They are independent of what S you choose, okay, at A, and this you make it satisfy the equation. Then what happens? So this particular solution corresponding to S2 parameterized with S is equal to S2 satisfies the system with a certain epsilon. Why is it so? See that XST is a solution of this system. So XS1T is a solution of the same system with S replaced by S1, and XS2 is a XS2T is another solution of the system with S replaced by S2. So what you are asking is, what about this XS2T as a solution of the system with S is equal to S1? Then you see that there is an error, because you have to replace these functions by the corresponding PNT, S1A, because this here SA will be coming, and when you use XS2T, it exactly satisfies the same thing with S is equal to S2. Okay, but if you look at the function, look at the solution XST, S1T and XS2T, they satisfy two different equations. So you are asking what happens to these functions as an approximate solution of the same equation with S replaced by S1. So you have two equations now. One, the set of equations with S is equal to S1. The other one, the set of equations with S is equal to S2. And we have the corresponding solutions here. So you are asking what happens to x as 2t as a function that is made to satisfy the equation. You know, it won't satisfy exactly, because it would satisfy the equation, because what happens is you see, you will have to do some correction here. Correction is what? See, it satisfies the equation with S replaced by S2 exactly, but with S replaced by S1, what will happen? There will be an error, because these are all continuous functions, very nicely defined. So there is an error which goes smoothly to the other one. The error will go to 0 when S1, S2 tends to S1. Okay. Since PI's are continuous, and Xi's are bounded as S2 tends to S1, this error epsilon tends to 0. So that is the conclusion that we make, because it's quite easy to work it out, because if you write the solution as x s1t for the one with s is equal to s1, x s2t as the solution for s is equal to s2, and then you estimate, see, you get two functions, f x t, I'll put the parameter as s1 f x t with the parameter s2. So you have two equations. These are the two equations, and the corresponding solutions are denoted by x s1t, and this is denoted by x s2. Okay. Now what happens if you look at this as a solution of this one? What you get is something like this, dx by dt. Let me rig it. S1 I change this simply by, okay, So xs1t is a solution, is an exact solution of this. But dx by dt equal to f of x t s2 plus a term which involves f see this part, you see this xst s2t satisfies this. Okay. So what about, there is an error. So there is an error term. What is the error term? So you see that f of x, okay, dx s2t by dt minus f of xs2t I will taking. So I can estimate this, and this error is less than or equal to epsilon. What is this error coming? The error coming from the difference of these two. So it is the norm of f of x t s1 minus f of x t s2 that comes. And there you see that pn's are all continuous functions, and therefore you see that the xi's are all bounded, so use that. So there is some error. So this is something like is less than or equal to epsilon. So this is less than or equal to epsilon, because these two are, because of the continuity and the boundedness, you see that this is less than epsilon. Okay, so that is the estimate. And after this estimation, what you see that one is an exact solution of the equation, the other one is an approximate solution with an error epsilon, and therefore you see that using that our fundamental theorem, so using fundamental theorem, one is an approximate solution, the other one is an exact solution, goes to 0 as S2. Okay, and this happens uniformly in T. So using this fact, we get, you see, now Ks T, this is the Green's function that we have, is related to this xst. Okay, in fact the first component of that. Okay, therefore, which implies, so Kst therefore Kst, therefore Kst and its first n minus 2 derivatives are continuous, at s equal to t also, which implies they are this is the first n minus 2 derivatives. What about there is a jump discontinuity along this. So what you have is this. Suppose this is AB. This is AB cross AB. This is T. This is S. So you see that this is AB cross AB. So the function as well as all its n minus 2 derivatives with respect to T are continuous. Across S is equal to T. And it's also true as a function of S. Further, there is a jump discontinuity for its derivatives, the n minus second derivative, n minus first derivative along S is equal to T. So that's the theorem that we have proved. So that's how you prove it, because you bring it down to the same interval. Otherwise what happens is there is a problem how to get this, connect this S1 with S2. Okay, so this theorem will enable us to prove the main theorem. Now we can write down the main theorem and then prove it. It's quite easy to prove. This is the main theorem. The solution xt of the non-homogeneous equation zero satisfying the initial conditions I equal to n is given by so this is the main theorem. So this gives the solution. So once you get the Green's function, you see that whatever q you have, you just put in and evaluate this integral. That will give you the solution of the problem. That's why I said it's a machine. And k generates a particular, what is called the kernel of this integral is the machine that produces the function x. If you recall our picture of putting the function x and then getting out Lx, and you want this Lx to be equal to minus q, And that's the question that you are asking. What is the x that you have to take so that Lx is equal to minus q? And the answer is this. Once q is given, you can run the machine in the backward direction, and this is the machine, this is how you run the machine in the backward direction, and k is the kernel of this, the main working unit of this machine. Okay, so you put your q inside this, integrate it, you will get a function of t. That function of t will be the solution of the main problem. This is the Green's function method. Okay, so let us prove it. Proof is by the previous lemma. Xt is well defined. Now kst, since kst and its derivatives with respect to t up to the order n minus 2 are continuous, we may differentiate under the integral sign. T obtaining, this is what you get when you compute this. You get x j minus 1 at t equal to integral the differentiation with respect to t j minus 1 st So k derivative with respect to t of order n minus 1 has a single discontinuity at t equal to s is equal to Now we observe that, see, we put it in the two portions. Okay, then what happens? Now you see that Ki n minus first derivative for s greater than t. S greater than t, that means t less than s, is identically equal to 0. That means on this portion the function as well as all its derivatives up to the order n minus 1 vanish identically. Okay. Therefore, the integral that you get would be the n minus first derivative would become integral a to t first derivative with respect to t of ds. So this sub t indicates you are differentiating with respect to t. Okay. Now since the integrand is continuous over the whole range of integration, what we obtain is this. You have xnt, this is equal to integral a to t plus n minus first derivative t equal to s plus 0, it means s is equal to t minus 0. Okay. So what you have is this. When you differentiate this, okay, so you take the nth derivative. When you take the nth derivative here, you can do it in the usual way, but what happens is there is a jump discontinuity at s is equal to t minus 0. Therefore, that gives this. So you are, you see, you are taking this and integrating. Then what happens is you will get this extra term coming. So you have got the differentiation with respect to it. So you, when you differentiate it, you see you have got this t occurring inside the integral as well as at the limits. That is why you get this extra term. Okay, so that is clear. It should be, it is coming in the limit as well as in the inside the integral or the on the integrand. Therefore, you get this term. And what this gives you? This gives you okay, we'll see. Now, k n minus first derivative this is equal to k derivative of st. See, at s equal to t minus 0 corresponds to t equal to s minus 0. So that's s plus 0. And that you know is equal to minus 1. Therefore, and you also have this identically 0 outside that, so you can make from a to t and t to b, and that is going to be identically 0. So I can replace this by a to b qt. So we have calculated the nth derivative. Okay. Now it is easy to work out this. So you work out this one. Therefore, you have to work out LTX. You substitute in that and then compute this. See, this is the only term that is coming out. All other places you see that. So you are left with this a to b L T K qt. But what about this? This is equal to 0. Okay. Therefore, since LTKST, because we have looked at the solution, the property of the function, and we know that that is equal to 0. Therefore, you get that zero. It is for S belonging to AB, because it satisfies the equation. Okay, we have that completes the proof. Okay, now one can easily verify that the initial conditions that comes from the definition of KST. Okay, so that completes the proof of the theorem. I think that is the right time to stop. Okay. We may make a couple of remarks later on this, but for the time being, let me leave you here. Okay. Thank you very much. Hello. Is there anyone there? No, I think all of you have left.